apply for this stuff. While in the undergraduate years, it is considered for. What's going on? Tech support? Yeah, support. May I ask you to share the content from the computer? Computer to the mainstream. So let me collect your.
So you said it's easier to get the GRFE while you're an undergrad, but you're thinking about to go to grad school?
Yes, because you are telling what is your. No, you have something. You are changing your grade substantially. And right now I'm going to distribute answer key, so it's there is no chance to get that. But okay. But at this switch there. Yeah. I definitely see highly talented people in the audience. When I was doing the answer key, it took me like 6 pages, and some of you were able to fit it in 1 page. So definitely a sign of a talent. So what I'm going to do is to give some codes and symbols and hide your names.
Oh, that's what yeah. We did that together. That's the part. She likes a lot. It's like that thing. In Star Wars, she like goes down to the dark side place, and then she's like looking in the mirror, and there's a whole line that shows it. Yeah. So I think it's like that's what they call it. You can't see that? I would hear this.
So I'm going to distribute your homeworks back to you, and then you will be grading yourself. Give me a sign if by mistake I distribute your own work to yourself. You recognize it. It's not you. Oh. Good.
I like how you go full down. You know, I'm that's how you're supposed to do it. So far into it.
Didn't know I picked.
I know definitely it is not you. You need to like give your share by grading. But I don't know. You design special homework for you, which will be 2 times harder. It's not you?
No.
Okay, I'm close to success.
I wish this was me.
Huh?
But I wish this was me. It looked a little detailed.
This is not you.
It does. I didn't staple anything, so it's not me.
Okay.
I think I know it's not
Last
me.
chance to mess up. Not you? Good.
I
So,
know this is me.
my printer didn't copyright, so I have only a few keys printed right now, but I will show it on the board and give instructions. So there are about 4 copies. So if you consolidate, you can just share.
I just threw my phone on the floor.
2.
Yep.
You can happen with me and Joe. Or Joe's going with him, so you can happen with me.
Okay, so here is
Where's 0? Where's
please correct me if I'm wrong with arithmetic. 40, 40, and 20 should be 100, right?
pose?
Okay, good.
Don't worry about 0.
So the problem number 1, if you identify that integration can be split on 2 intervals, 10 points. If the first term is found 5 points. If someone identified that all 8 terms by the cosine are zeros, another 10. If someone got the answer in front of B1 coefficient in front of the first sign, another 5. Just keep doing. I'm going to collect in a couple of minutes. Do not read on all details. Just scan the. If someone did identify that expansion coefficients in front of signs are alternating and are zeros or non-zeros for even and odd, another 5. And if there are complete answer, like 1/2, 1 over pi for first sign, and skip the 1 over 3 pi for the third sign, and then 1 over, and then it keeps the progression. It's full credit 40 points. So try to be liberal and give more points at any opportunity. Give benefit of a doubt.
Okay.
So you know, instructor is giving a grade to himself. Grader also. It's your benefit if you give higher grade. Try to.
We all give ourselves.
Well, I will be a little surprised if you give over 100 to someone, but if you see good attempt, just go ahead.
Do we give them plus 10 extra credit points for answering question 0?
Yes. Yes.
Okay.
Are you still working on number 1? Lift your hand and give me a sign if you need to flip back to the previous slide. So we will be done with grading in like 5 minutes. Yeah. Oh, you're charging his own. Yeah. I was thinking of yes. No. And if you have pens with different than regular color, something exotic like red or green, it's better, but it's not mandatory.
So
Some of you decided to go only with numerical solution, which is also fine. You cannot give like full 40, but give some. If the strengths, the B coefficients are alternating, and some you were able to find it numerically, then give partial credit. So just be generous.
alright. Actually did not. Oh,
Or anyone is not, please lift hands if you're not done with grading problem 1. Only 1, so the rest are fine to go further.
Yeah, here's. I'm just.
no, it's problem.
This is 3.
This is
That's all I got. Right? 'Cause this is.
Okay, so
This
I
is
only got
3.
this is this is 20.
Yep.
someone didn't submit.
Mine only has problem 1.
No.
No? Oh,
Because then
well.
this is.
Okay,
Yeah, was this just 3 then?
it's
Yeah.
So,
okay. Going to problem 2. 20 points, and it is basically repeating stuff that we had in class. So kinetic energy, operator of energy if there is no potential energy, second derivative 5 points, plane wave definition also 5 points, and then if you are plugging in the plane wave under the Hamiltonian operator and reproducing plane wave itself and this h bar square k square over 2m, another 5 points. Oh, and if you write eigenvalue, another 5. So I think everyone should get full credit for this, right? I cannot imagine anyone missing it. So if you split problem onto several steps, add together partial steps and make circle for the whole problem. Okay, and for the third problem, first I'll give suggestions how to grade it if it was analytical solution. So if someone just reproduced the task in mathematical form, already give like 5 points. Then if there was an attempt to convert this integral into to identify full square, just attempt, even if it was not successful, give generous 15 points. Because it's not a math class. You just, if you follow right logic and fail in some minor steps, that's fine. Then if the person whom you're grading was mathematical genius and was able to identify the full square, give another 5 points. And if upon getting full square, a person whom you are grading was making an attempt to convert it into Gaussian integral by changing variables, just attempt to change variables, also rewarded with 5 points. And if he or she, well, she's not, if the person who is here remembers that Gaussian integral is square root of pi, give another credit. And then, if the answer looks like a Gaussian function in terms of k variable, so minus k squared, with the rest of factors looking approximately like this, give full credit. So just go to the last page. If you see something similar to this, give full credit. If it is not really this, then seek an opportunity to increase the credit. Like if the person is given numerical distribution showing the Gaussian shape, like give maybe like half of credit if there is nothing else. If there or if there is a verbal explanation that
Not sure.
Is there not Joe? Good Joe? Joe?
C sub k exhibits Gaussian distribution. Give credit. Good.
Does it say anything, Joe?
Anyone needs more time? Lift hands if you need more time.
Foolish.
No?
So,
40, 20 for each problem.
so there's 40, 20, 40, right?
40, 20, 40. First and last are 40 points worth.
And then 0 is 10 extra credit?
Yes.
Okay.
Is someone getting 110?
So let's give 100 up. 100 up.
Okay. Anyone needs more time? Okay, I'm going to collect. Put the sum total near the at the top.
I like this page. I like this page.
So you were not super serious.
I didn't know what I had.
Okay, thank you for attempt.
Jared?
Okay.
Is it out of 100 points? We did a 10 for
Mm-hmm.
10 bonus.
Yep.
Yeah.
Good.
You
Thank you much for
want
making my life easier, and I will go through and basically approve. But then, if someone is not happy with the grades, I will keep in secret who was a grader. But you know that you cannot blame me. Okay. So what are we doing? Oh, let's scroll back to the MATLAB stuff. What is, yes. Who was volunteered to cover missing points?
Oh, me. I forgot to send you an email.
Okay, repeat your name, please.
Isaiah?
Okay. Vectors?
Yeah.
Very
My
good.
bad.
Huh?
My bad. I forgot to email you.
No, not a problem. Not a problem. And probably we'll split these three things between the first two speakers. Like making break somewhere like here.
Man, does that mean I get eigenvalues?
Huh?
So I need to sign up.
You didn't sign up yet? You do want eigenvalues?
Well, no, but that's what's left.
It's okay, I got the part.
Joseph?
Yes, Joseph.
Okay, I'm making progress. My goal is to just remember all your names by the name of the course. Then it will be my success. Well, eigenvalue is the hardest part of the overall, all of them. And if you are not typically attending Wednesday night lab, next time, please do. I'll cover this subject. So it will make it much easier. Okay, then we are good to go. So next Friday, this time, You will be talking and I will be sitting and enjoying. If you don't mind. So, who we are and what are we doing? We all were decepted by an idea that we are here for chemistry and physical chemistry, but later on we came up with an idea that we need quantum theory because electron has wavy motion, and later on, tech support. I'm going to focus on the screen, and just if I fail, you need help. Okay, I think I'm super successful today. Good. Help is not needed right now. Thank you for backing up. Good. And later on, it turns out that we do a lot of mathematical background because otherwise it's hard to go forward. So, in some sense, it's physical chemistry with elements of linear algebra, differential equation, calculus, and scientific programming. I hope you want, or at least you can predict the future, right? You know how to do it. And there are about 3 ways. First is unpractical, just philosophical for evolution operators. Second is numerical for propagating forward in time by computation. And the third one that we were practicing in the previous lecture for wave function developed as superposition of all eigenstates multiplied by expansion coefficients and multiplied by phase accumulation factors that do depend on eigen energies, right? E sub k. And there are proofs that this construction gives you a function of the future. But why are we doing it? Is it only the reason to torture young minds? And no. Do not give this answer in public unless you are in a very tight circle of close friends. The goal of this thing is practical, is to back up experimental measurements, characterization of materials, molecules, and their properties, right? So when you are in the wet lab, you often have instruments where you put your sample, push some knobs, turn them, and then on the computer or on a piece of paper you have some graphs. And you're saying, oh, those are my observables. I'm getting highest grade, or I'm publishing a paper about this, like graphs, spectra, or whatever you measure. So the goal of physical chemistry in general and quantum theory in more narrow is to predict outcome of such measurements, predict this observables as function of whatever you change by theory, or at least pave a way how to do it so that we get back up an idea of what is going on. So you have seen scientific instruments like spectrometers, NMR devices, thermometer. The scientific instrument everyone has seen, right? Did you ever had an instrument to measure wave function? Or heard of it? You did?
Spy a radiometer. Would that measure wave functions?
No.
Okay, never mind that.
No. It's wave function of an electron.
Oh,
It's
no.
not the distribution of electric field in space. Or if electric field in space, you know, there are radars, right? Which measure back electric field after it is scattered from something. And there are these mini radars to find beams when you do construction. Have you seen those? No? Sometimes a couple of people in the class do have experience in building something. So if you want to drill in a wall, if it is just thin. Huh?
Stud finder?
Yes, stud finder. So it's basically a mini radar. The electromagnetic waves reflect from the start and then identify it back, and then your lamp is flashing and sound is being used. But it is for electric field, not for electron. I'm not aware of any instrument to measure wave function. If you get one, you'll be a famous scientist with glory. And generally, finding wave function is not a goal of this course of physical chemistry. The goal is to find observables, which are something much more practical. Wave function is, to some sense, it is mathematical abstraction, which may or may not exist. Well, it does exist. We have equations, but it is not literally what we hold by hands. The goal is to find observable. And there was it's an interesting aspect for history of science. At the beginning of 19th century, there were a lot of big brains who were trying to address challenging and design new equations. They were sometimes friends, sometimes enemies, well, scientifically, arguing to each other. And one of these persons was supporting an idea like, we do not need wave function. It will torture students in the next centuries. If you need observables, let's write equations for observables only. And we are going to cover this subject today at the start. That's it. It will be a fourth way to predict future. Predict future not of any future, not wave function, but only future of an observable. So, what did we? I was not reading what I have written a year ago. So if I start reading, I will be surprised. But what did we got? Where did we stop last meeting in accumulating lecture material? We were drawing bars,
Yeah.
vertical, horizontal, talking about transpose and Hermitian, right? And last thing we were talking about moving backwards in time. Okay. And no one was objecting that all operators that come up in quantum theory are Hermitian, which means if you apply complex conjugation and transpose to an operator or matrix represents an operator, it will be equal to itself. Right? So Hermitian conjugation of Hamiltonian will be Hamiltonian again. You either do not care or enthusiastically support it. So no one was telling, no, I do want new science with non-Hermitian Hamiltonians. H dagger equals H. And for most of operators, one can do the same. So, what is an equation for observable? Again, I do not remember all of the names of the class, and I have already forgotten who was presenting me, but it was like postulate number 4 or 5, like about observables.
I did 5. 5 and 5.
So how to get an observable if you know wave function and you know the operator? Can you declare this equation by what?
Probably could earlier. Can't get off the top of my head.
Anyone can? Try to write it in your notes, your best guess, and then I'll try my best guess, and then you compare. So, expectation value is typically symbolized by angular brackets, and then we do have wave function, given position, given time, and we do have quantum operator that would correspond to the observable. And we need to combine wave function and operator in such way that if you generate the value of observable that comes out from the apparatus, from the instrument. Anyone got an integral in your equations?
No, you.
Okay. Asking once again. Did you ever got integral in your answer?
No, I do.
Okay, at least that's good. So try to stick it somewhere. Did you got wave function in your answer? How many times?
Well, I got that once and I was conjugate once.
Did you hear it? So twice. Once itself, once conjugated. And the integral. Over time, over space. I would say over space or whatever variable is. Did you put the operator in your equation? Right? In the middle. So if we wouldn't have integration and operator, it will be just probability density. But if in the equation of probability density you stick inside the operator and put integration up front, it will be expectation value of an operator, and typically it is a bridge to go from this abstract world to real world, so observable. So it is what comes out of instrument. Well, now we are too general and abstract. One needs to very specifically tell how to construct operator for each specific measurement. But generally, this rule holds again and again in any circumstance. This is the thing that you silently supported and accepted last time. That if you have normal wave function, Hamiltonian acts from left to the right, and if you have conjugated wave function, Hermitian conjugation of Hamiltonian, which is equal to Hamiltonian itself, acts from right to the left. Especially if you convert wave functions and operators into matrices, it becomes very evident.
So both those equations right there are equivalent, or not?
Well, this one generates kind of time-independent Schrödinger equation for wave function, and this would be Schrödinger equation for conjugated wave function. Right? So they're equivalent in a sense that it's conjugation. And conjugation of energy gives nothing because energies are always real. Right? There are some crazy theories with imaginary energies, but we are not touching them in this course. It's like extra. So, what if we try? So, our goal is to predict future, but we want to give up wave function and predict future only for observable, expectation value of observable. If you want predict future, means that we need to formulate dependence on time. And the first step to find dependence on time is just to set up differential equation. And even simpler way, just to apply time derivative and check what it will be. So d dt applied to integral dx psi star e psi. Can we swap order of integration and differentiation? Not always. If it is applied to the same variable, then I'm not sure. But if the integration is over one variable and differentiation is over another one, then we don't care which goes first. So it's completely normal to swap them. Integral dx dt psi star e psi. So this is product of three functions, each of which may or may not depend on time, right? How do you formulate derivative of product?
Like rule?
Product rule. Let's practice it. Try. We don't have time. This is very short course. Otherwise, I wouldn't get someone to save no effort. Keep eating the dx. So product rule to product of. Probably if it is product of 3, there should be 3 terms. Right? So first d psi star dt multiplied by unchanged a times psi plus psi star derivative over time is applied to operator times psi plus psi star multiplied by psi star a capital multiplied by ddt of psi without psi. Right? It is what you have written yourself. Product rule. And generally, operators may depend on time. There is nothing wrong with it. Actually, it is fun to deal with time-dependent operators. And we may do it in the last 2 weeks of the class. But for now, let's assume that operators do not depend on time and we drop the middle. Again, we are pursuing the goal to predict future, not of everything, but only of one observer. To have less torture on young minds to achieve the goal quicker. Why should we carry information about multidimensional wave function if we need just one number, one function? So, if we are applying Hamiltonian to normal wave function, it is a natural part of the usual time-dependent Schrödinger equation. If you would start solving it, at least start to solve for time-dependent part, you'll see that phase accumulates with minus IH bar Hamiltonian times t. If we apply Hamiltonian to the from right to the left, it will be time-independent Schrödinger equation for conjugated wave function. Time-independent Schrödinger equation for conjugated. So we are kind of approaching main conclusion from 2 sides, from 2 aspects. One side was equation for observable. Another one is discussion of the Hermitian property of Hamiltonian and propagation in time, forward or backwards. So if you solve this equation, time-dependent Schrödinger equation with conjugation, we will see that it will accumulate phase in the opposite direction, which is equivalent as normal solution, but with negative time. Right? So if you have this opposite thing start here, it means we just travel backwards in time. Good. What is the connection between previous handwritten slide and this machine typed slide? Yes?
We have the derivative of wave functions on both sides.
Yes, exactly. Yes. So we have equations for derivative of normal and conjugated wave function on this slide. And on the other slide, we got derivatives of wave function as a result of product rule. as a component of the equation in the product rule. So why don't we try to plug them in and see what happens? And why are we doing it? What is the goal? The hope is to get an equation where left and right part will contain only angular brackets of A and get rid of wave function completely. I probably should tell it up front. So make an equation that doesn't have wave function, only expectation value of operator A in angular brackets. So I will take a risk of writing it myself, and then probably I have already prepared answer before. So we do have integral dx, and here we have d psi star dt times a psi plus psi star a times d dt psi. So these are two things that we can plug in. So when it was time derivative of wave function, we can plug in minus I over h bar h over psi, right? Because this is TDSE, time dependent equation. When you had stuff with star, we can replace it by plus I h bar psi star h. So this will be time dependent equation for conjugated wave function, and it should be Hermitian sign here, but Hermitian conjugation of Hamiltonian is Hamiltonian itself. So plugging in and continue to roll this equation. T. The hope is that right part can be convoluted into some expression of this A in angular brackets. Yes. Well, I can put I over h bar to the front, because this is a just factor of the brackets. And now here we have psi star h a psi. And here we have minus psi star a h psi. Right? So here was operator of an observable, and here we are getting the Hamiltonian.
Shouldn't the h in the first part of that expression be the conjugate?
Yes, yes, we can always put it just a little memory of what we are doing, but h dagger is equal h. Good. Nothing cheesy, nothing straightforward. Almost last step. So, if you are chatting with your friend or sending an email and you want to express that something is very ridiculous for you, how do you transfer laughter in typing?
Emoji.
Huh?
Emoji.
And if you do not have emoji,
Oh wow.
like wahaha. I don't know. Maybe you're doing it in a different way. But see here, ha ha ha. So it's a laughter equation. So, what if we call this HA as a new operator, maybe not A, but B is tilde, and this AH, another B. Then, if you consider just this pair of operators as one operator, then see, it is the same construction, integral over space, wave function conjugated up front, wave function without conjugation after, and here is an operator, right? So the stuff here, it will convert into the just angular bracket of this operator B or angular bracket of the HA, right? Expectation value. Here will be the expectation value of HA, here will be the expectation value of AH. Okay. I thank myself for typing. We already did it, right? This conjugation, without conjugation, plugging in Schrödinger equation. And now we have this protocol for finding expectation value, but we have subtraction of two operators. So this construction can be replaced onto expectation value of HA minus expectation value of AH. So time derivative of the expectation value of an operator that we may need for experiment is imaginary unit over H bar multiplied by bracket subtraction of expectation values of two new operators obtained by multiplication of Hamiltonian onto our operator of interest. Okay? Nothing wrong. Now, here we come to special features of quantum theory. Remember that operators cannot be swapped, or not always can be swapped. So, if we remove dagger and it will be not operators but regular numbers, HA minus AH will be 0, right? But if those are quantum operators, or matrices, swapping the order will make this thing non-zero often. Sometimes, for some operators, it will be 0, but for many of those, it will be not. And in order to find our goal, to find equation of motion for the expectation value of an operator, one needs to perform this quantum commutation of operators. And very often, it converts into another observable. But then this second observable is often naturally connected to the first one. So one is, it's rarely if you get only one equation, but typically one gets system of couple of equations that are connected to each other and are much easier to solve than actual Schrödinger equation. There is a way to bypass this live without wave function. So we accept its existence. We use it as an abstract concept to derive equations. But there is a way to fulfill our goal, to predict outcome of experiments without having any guess about how a wave function looks like. We can formulate equations only for expectation values. T, T, P, P bar, H, minus H. And this subtraction of H, one operator minus another, this laughter operator, I don't know, maybe when creating quantum theory, people were not so numerically informal. I would call it after operation, but they call it commutation, because swapping order. Commutation. So, and it is symbolized by square brackets. So square brackets and comma means aha. HA minus AH. So the guy who designed this equation, his name is Heisenberg, and he was opposing to Schrödinger, telling, well, I do not know literally how they were arguing. Come on, who needs a wave function? Just solve my equation, and life will be easier. Well, it's only my projection. And there is an immediate consequence of this equation where we can connect to real life without solving anything. So if you would find such quantum operator, such variable, such observable, for which quantum operator will commute with Hamiltonian operator, meaning this subtraction will give zero, like zero operator, then it will mean that time derivative of expectation value equals zero, right? Which means expectation value of such observable will not change in time. So it will be constant forever. It is why in my undergraduate course, I got B in quantum theory. The question was like, in which circumstances observable doesn't change in time? And the right answer, when its operator commutes with Hamiltonian. And I don't know why I was not. When it commutes, for example, with Hamiltonian. No, only with Hamiltonian. I don't know, do we have time or not, but I'm over 6 minutes. I thought that if they were just 10 slides, it should be quicker. So, no homework for this weekend, because you need to accumulate strengths for presentations. No, you can have it for good memories. Have a good weekend. You too.
Yo.
I'll stay here just in case there are questions.
Oh, nice. Yeah.
I'll put it off the record.
I-